part D asks us to find the times and positions where the particle changes direction. Changes direction. Now, for the particle to change direction, it had to stop. And stopping means the velocity is equal to 0. So to find this, to find where the object, or at what time the object changes direction, we need to find the times at which the velocity is 0. But we already found this in part A. So v of t is equal to 0 at t equals 1 or 2 seconds. That means there were 2 changes of direction after 1 second and after 2 seconds. These are the times where the object changes direction, but where is it, or where the position is at that time? So to find this, we need to find s of t, or s of 1, and s of 2. If you substitute 1 into s of t, you should get 6 centimeters. And if you substitute 2 into s of t, you should get 5 centimeters. That means the object changes direction after 1 second when it is 6 centimeters to the right of the origin, and after 2 seconds when it is at 5 centimeters to the right of the origin. The next part of the question asks us to draw a diagram to illustrate the particle's motion during the first 3 seconds. To draw a motion diagram, you need to know 3 things. You need to know the initial position, where a change of direction happens, and where the position of the object is at the end of the period, which is in this case 3 seconds. From studying the initial conditions that we looked at earlier, remember that s of 0 was 1 centimeter to the right of the origin, and v of 0, the velocity, was 12 centimeters per second. A change of direction happened at t equals 1, and s of 1 was 6 centimeters, and another change of direction happened at t equals 2, and s of 2 was 5 centimeters. So these are the initial conditions. This is where a change of direction happens. What is left for us to know now is where the object is at the end of the time period, which is s of 3. If you substitute 3 into the displacement function, you should get 10 centimeters. Now to draw a diagram now, we draw a number line. And we locate the origin. So let's say the origin here is O. And then this is 1 centimeter to the right of the origin, 2, 3, now at t equals 0, the object started its motion 1 centimeter to the right of the origin, and looking at the velocity here, it has a positive sign. That means the object was moving to the right. So at t equals 0, s was equal to 1. So the object started here and it was moving to the right. But then after 1 second, when the object was 6 centimeters to the right of the origin, the first change of direction happens. So after 1 second, when the object was at 6 centimeters, the first change of direction happened, and then instead of moving to the right, now the object is moving to the left. And then after, at t equals 2, when the object was at 5 centimeters to the right of the origin, another change of direction happened. And then after 3 seconds, the object reached 10 centimeters to the right of the origin, and that's where it ended at the end of the 3-second period. So this here was at t equals 0. This here was at t equals 1, and then t equals 2, and then that here is at t equals 3. This is what describes s of t, the motion or the position of the object with respect to O at any time t. Now remember here that we're discussing motion in a straight line, so actually the object is moving in a straight line going backward and forth, but we draw it like this just to be able to illustrate the change of direction and see clearly how the object is moving. The last part of this question is asking us to find the total distance covered by the particle in the first 3 seconds of motion. So, because we've already drawn the motion diagram, finding the distance covered in the first 3 seconds is going to be easy. The object started here, it moved from 1 to 6, that's 5 units, and then came back from 6 to 5, that's 1 unit, and then from 5 to 10, that's another 5 units. The total distance traveled would be 5, then plus 1, and then plus 5, which is 11 centimeters in total, and that's in the first 3 seconds of its motion.